The electrical properties of 2D transition metal dichalcogenides are largely what mark them as such a great scientific breakthrough. It is because of this that this video will be exclusively discussing these electric properties. 3D TMDs have an indirect bandgap. However, the moment that the material is reduced to its two-dimensional form, it obtains a direct bandgap, which is a very useful property. From a graphical perspective, a direct bandgap material's conduction band's energy versus momentum graph moves at the same rate as its valence band's energy versus momentum graph. In practical terms, when a material has a direct bandgap, it means that its electrons can absorb energy and release it without any other requirements to transform this energy from one form, for example light, to another form, for example electricity. Indirect bandgaps, on the other hand, have a much lower probability for an electron to be excited by light to create current, for it requires, in addition to a photon, a phonon to align the valence and conduction band. Silicon, which is commonly used in modern solar cells, has an indirect bandgap, hence the heavy reliance on other factors such as doping for it to conduct electricity. Equally important as the presence of a direct bandgap when discussing photonic properties of a material is the size of the bandgap. The bandgap is measured in electron volts, and it gives the amount of energy required to excite an electron within the material. Insulators have very large bandgap values, while conductors don't have one at all. Semiconductors have low values for bandgaps. 2D TMDs have rather large bandgap values compared to commonly used semiconductors in modern society. For example, molybdenum disulfide has a direct bandgap value of 1.8 electron volts, while silicon has an indirect bandgap value of 1.12 electron volts. Although it means electrons must gain more energy in order to generate current, having a large bandgap isn't necessarily a bad thing. Wide bandgaps offer a number of benefits, such as the ability of a material to function under conditions with higher temperatures, voltages, and frequencies. Thus, a wide bandgap gives a material more applications, as well as potential to become more efficient. One last benefit of a wide bandgap is that it gives the material the ability to absorb a wider range of light to excite an electron. 2D TMDs absorb more light than silicon, as they take up the entire visible light and near-infrared region of the electromagnetic spectrum. As a result, 2D transition metal dichalcogenides show a number of unique properties that could be implemented to enhance the generation and usage of electricity in our society.